All right, in Chapter 12, Section 5, we're going to look at lines and planes. The first question is just a series of true-false questions. And I'm not going to try to draw these. You kind of visualize it. If you want to draw them to help you, you can. So it says two lines parallel to a third line are parallel. So if you can imagine in 3 dimensions, any line, any other lines that are parallel to it, even if they form, some kind of circle around it, will also be parallel. So that's true. 2 lines perpendicular to a third line are parallel. So that's false. So there's lots of ways you could draw perpendicular. I said I wasn't going to draw them, but there's too much of a temptation. Let's try it. So 2 lines perpendicular to a third line. So here's a line, and I can have a perpendicular line going down like this, and again in 3 dimensions, you could have a line coming out like that, and this is 90 degrees, and this is 90 degrees. So you got a line, and you got one going down, and then you got one going off at some angle, but it could still be 90 degrees based on the plane that it creates with the blue line. Okay, C, 2 planes parallel to a third plane are parallel. So that is true. So if I've got 2 planes like pieces of paper that are parallel, and then a third one is parallel to the first one, then these 2 have to be parallel. Two planes perpendicular to a third plane are parallel. So I can make that exact same argument. In fact, I wish I didn't erase this, so let's put this back. Now just imagine that these are planes. So here's the red plane. It's perpendicular to blue. Here's the purple plane. It's perpendicular to blue. And now let's make blue a plane. So here's the blue plane. And red and blue are perpendicular. Purple and blue are perpendicular, but purple and red are not parallel. 2 lines parallel to a plane. So E. So D was false because I kind of just drew a picture that kind of refutes that. E, 2 lines parallel to a plane are parallel. So this one is also false. If I have, so 2 lines parallel to a plane are parallel to a plane. I mean, there's lots of ways you can be parallel to a plane. So I have this green line out here. Imagine it's not on the blue plane, it's above it, but it's parallel to the blue plane. Okay, but it's not on it, it's above it. And then I have, let's say I have this orange line over here, and it is parallel to the blue plane, but not on it, so it's above it. Notice green and orange are not parallel. So that one's also false. 2 lines perpendicular to a plane are parallel. Okay, so let's use purple. That could be easy. So here's purple plane. Anything perpendicular to it, let's say we'll go straight up. So there's a perpendicular line to the purple plane. Well, any other line I draw perpendicular to that, so let's draw orange. Let's say it goes straight down like this. That's perpendicular to the purple plane. Well, notice green and orange are parallel. So any orange vector I draw, any green vector I draw that are perpendicular to the purple plane are parallel to each other. So that one is true. Last one, G, 2 planes parallel to a line are parallel. 2 planes parallel to a line are parallel. I mean, the idea that lines and planes are parallel is a bit silly because Again, let's just draw a line. There's my blue line. I mean, technically, any plane I draw can be parallel to this thing. So, here's a red plane that I draw. Now I don't have to draw the lines like that. This is parallel to the blue plane. Okay, you got to think in 3 dimensions here. And then in an orange plane I draw, it can be at an angle. Let me see if I can do this. Again, it's hard to draw in 3 dimensions. This one is at an angle to the red plane, but it could still be parallel to the blue line. So that's false, because clearly orange and red are not parallel. Okay, so look at those, think about them. If you want to try to sketch these out and think about it, it might help, but it is hard to draw. Oh, I guess there's even more. Okay, so H, 2 planes perpendicular to a line are parallel, so that would be true. And then 2 planes either intersect or are parallel, that's true. 2 planes either intersect or are parallel, that's false. And a plane and a line either intersect or are parallel, that's true. So again, trying to draw these is a real bear, so I'll let you kind of think about why those are true or false. Okay, 2, find a vector equation and a parametric equation for the line. Use the parameter t. Okay, so this is a little less abstract thinking. So the equation is, if you have a vector r, it can be broken into a kind of a starting vector or a point plus t times some vector v. So we're going to make this is a point right now. To make it a vector, we just have to subtract it from the origin. So we can just write that as 8, -9, and 2. And then the vector v is 1, 5, so it's going to be plus t, 1, 5, -2/3. And what we want to do is actually write this in I, j, and k. So this is 8i. Let me not write the hat since my pen doesn't want to do it. Plus 2k. Plus, this would be 1 times t, so it's just t in the I direction. Plus 5t in the j direction. Minus 2/3 t in the k direction. So we're just distributing this t, but we're also putting the I, j, and k vector components on each number. Okay, then we're going to combine i's with i's, j's with j's, k's with k's. So this would be 8. This is going to match up with t. So it's plus t on the I vector, plus minus 9 is going to couple with 5t, so we'll call it 5t minus 9 in the j component, and then k is going to match up with the k, so it's going to be plus 2 minus 2/3 t on the k component. And that is the answer that I put here. Then they want us to write this as x, y, and z as functions of the parametric variable t. So we just grab this. So 8 plus t is going to be x. 5t minus 9 is going to be y. 2 minus 2/3 t is going to be the z component. So those would be the answers that go there for number 2. Okay, problem 3 is really not too bad. We're given an equation, 2x plus 4y plus z equal 8. And that's the equation of a plane. And it says use intercepts to help sketch the plane. So what we do is to find an intercept in 2 dimensions, we let one of the variables equal 0 and solve for the second variable. In 3 dimensions, we have to let 2 of the variables equal 0 and then solve for the third. So the first one we're going to find is x. So we're going to let y equals z equals 0. So both those are going to go to 0, and those second and third terms will go away, so you're just left with 2x equals 8, which solves to be x equals 4. So there's a point on this plane that has an x value of 4 and the other 2 values are 0. In fact, let's look at the correct answer. It would be this point right here. Okay, then we're going to let x and z equal 0 to solve for y. So we're going to get 4y equals 8 or y equals 2. So the point would be 0, 2, 0. And that point's right here. So it's 2 in the y. And then the last point, we're going to let x and y equal 0, and that should solve for z. So z equals 8. And so we get the point 0, 0, 8, and that point is right here. So it's straight up. And so that would be the correct solution for problem 3. Okay, for problem 4, we're going to have we want the line through the point 1, 0, 2 perpendicular to the plane x plus 4 plus z equals 4. So this is very similar to the last problem, or one of the problems we just saw, where it's r0 plus t times the vector v. Now I'm going to kind of skip a step here. So we're going to write this 1, 0, 2 as 1i plus 0j plus 2k. Plus, we're going to multiply this t into each of these. There's really a 1 here. 1, 4, 1. Actually, I better write that part. So the vector v is the numbers in front of the x, y, and z of the plane. So it's going to be 1, 4, 1. So when I multiply t by each of those, it would be 1t in the I plus 4t in the j plus 1t in the k. And I believe, okay, so I guess I didn't have to distribute that t. So this answer is the same as this answer, but they didn't distribute the t. So that's fine. And then they're going to combine like terms and call this 1 plus 1t, or t plus 1 really, in the I. And then 0j is going to match up with 4tj, so it's just plus 4tj. And then 2k is going to match up with 1t, so it's going to be t plus 2 on the k. And it's kind of hard to see because I didn't put spaces in between these commas, but you got 1 plus t there, 1 plus t here, 4t, 4t, and then 2 plus t, 2 plus t. So that's how those match up for problem 4. Okay, for problem 5, there's a general formula that says this. X equals AT plus x0. So in parametric form, x would equal that. And y equals bt plus y0. And z equals ct plus z0. And the x0, y0, and z0 come from any point. So this point 5, negative 3, 4 would be x0, y0, z0. So that's the point. So it says, I should have read the question, find parametric equations and symmetric equations for the line. Use the parameter t. The line through the point 5, negative 3, 4, and parallel to the line x plus y equals y over 2 equals z minus t. Okay, so the x0, y0, and z0 are going to come from that point, and then a, b, and c are the numbers in front of your x, y, and z. So this is 1 in front of x, this is 1/2 in front of y, and this is 1 in front of z. So that's a, b, and c. So x is just a, which is 1, times t, plus x0, which is 5. Y is just b, which is 1/2 in front of t, plus y0, which is -3. Z is c times t, but c is 1, so it's 1t plus z0, which is 4. And those are the equations I wrote right here. Okay. Oops, actually there's an error there. When it's written like this, okay, these are not A, B, and C. Okay, let me rearrange this. These all equal t. So the formula we actually need is this one. We need x minus x0 over a, and that should equal y minus y0 over b, and that should equal z minus z0 over c. Notice x plus 1 is not being divided, it's being divided by 1, so that's a. Y is being divided by 2, so b is 2, not 1/2. And then z minus 2 is being divided by 1, so that's c. So x and z are correct, but the one that's not correct the way I've written it here is this one. B is actually 2, so we would write 2t minus 3. And you can see those are the answers I have here. Okay, then they want us from these three equations to solve for t. So if I rearrange these three equations solving for t, for the first one I just have to subtract 5 from both sides. For the second one I have to add 3 to both sides, but then I also have to divide out the 2 in front of the t. And for the third one, I just have to subtract 4 from both sides. Okay, and then the answer would be this one right here. So those are the symmetric equations because they all equal t, the parameter. That's problem 5. Okay, problem 6. We're given 3 points and we have to find the plane through these 3 points. So we're going to call this point P, we're going to call this point Q, and we're going to call this point R. And then we're going to find 3 vectors, PQ, which would just be take the numbers in Q and subtract the numbers in P and put them in vector form. So you should get 4 minus 4 and 0. Then we're going to find PR. Take the numbers in R and subtract from them the numbers in P, and you should get 4, 0, -4. Then we're going to find the normal vector to these 2 vectors. To do that, we're going to find the cross product of PQ and PR. And I'm not going to show this since we did a whole section on this. Review your notes from section 12.4, how to do cross products. If you do this, you will get the following cross product vector. It's kind of an interesting one. It's all 16s. Okay, and this is going to equal A, B, and C. So those same A, B, and C letters we saw in the previous example. Okay, and then we're going to know or write that a plane is an ABC vector times the difference of x and some point on the plane. So we have A, x minus x0 plus B, y minus y0 plus C, z minus z0 equals 0. And x0, y0, and z0 can come from any of these 3 points. I'm just going to pick P. So let's make these 3 points, or these 3 numbers, x0, y0, and z0. So the plane would be A, which is 16, x minus x0, which is 0, plus B, which is also 16, y minus y0, y0 is 4, plus C, which is 16, z minus z0, which is also 4. And it takes a little bit of algebra. You have to distribute these 16s into all these numbers, combine like terms, and you should get 16x plus 16y plus 16z minus 128 equals 0. So 16 times minus 4 is 64 negative. 16 times minus 4 is 64 negative. Those combine to minus 128. Then you write that as add the 128 to the right hand side. And then it turns out you can divide everything by 16 and you get x plus y plus z. 128 divided by 16 is 8. And that's the equation of the plane. So just a little bit of work there, but it is, after the cross product, it is basic algebra, distributing and combining like terms. Okay, so for 7, it's really similar. It gives us 2 points and it says find the plane through the origin and the points 3, 4, 3, negative 4, 5, and 5, 4, 2. So let's call this, what did I call this one? I called this one Q and R, and I called the origin point P, which is 0, 0, 0. Now, the nice thing about this is when you do PQ, it is just these numbers in Q because you're subtracting 0 from them. So it just turns into a vector, 3, negative 4, 5, and then PR, again, just those numbers subtracting 0 would be 5, 4, 2. Then you do have to find N, which is PQ cross product with PR. Review section 12.4 on how to do this. You should get, for my numbers anyway, I get negative 28, 19, and 32. And that's A, B, and C. And then our plane is A, which is negative 28, times x minus x0, but x0 is 0. So if we smartly write point P as x0, y0, and z0, a lot of stuff's going to fall away. So the plane is A, x minus x0, plus B, 19, y minus y0, plus C, 32, z minus z0, but all those are zeros. That has to equal 0. And everything's going to distribute, everything's going to fall away pretty nicely. This is just minus 28x plus 19y plus 32z. Since there's just zeros in there, equals 0. And that would be your plane right there. Okay, for problem 8, it says, find the point at which the line intersects the given plane. So it gives us x, y, and z parametrically, which means that they're equations with respect to t, the parameter, and then they give us a plane that's just x, y, and z. So what we're going to do is we're going to substitute this in for x, 5 plus t in for y, and 2t in for z. So we're actually just going to replace x, y, and z in the plane equation with the parametric form. So x is going to become 1 minus t. Then it's minus y, but y is really 5 plus t. Then it is plus 5z, plus 5, but z is really 2t. And that's going to equal 4. So let me actually make sure this is clear. That was x, this was y, this was z. So from the plane equation, these bubbles I wrote in are replacing x, y, and z. Now notice this equation is just t. So it has t in numbers, which means we can solve for t. So this would be 1 minus t minus 5 minus t plus 10t equals 4. And if you combine like terms, you will get 8t on the left equals 8 on the right, which means t has to equal 1. Well, now you just back substitute that into the original problem. So now we're just going to put these back in to these circled equations to solve for x, y, and z. So x was 1 minus t, but now t is 1, so x is 0. Y was 5 plus t, but t is 1, so we get 6. Z was 2 times t, but t is 1, so we get 2 times 1, which is 2. So we get the point 0, 6, 2. 0, 6, 2. That's problem 8. Okay, problem 9. It gives us two planes, and we have to figure out if they're parallel, perpendicular, or neither. So we're going to create two vectors we call n1, which is just the coefficients of the x, y, z from the plane. So it's going to be 7, 28, minus 21. So I just got those from these red numbers in front of the x, y, z from plane 1. Then we're going to take n2 to be the numbers in front of the second plane, minus 24, 48, and 56. Then we're going to see what n1 dotted with n2 gives us. So if it gives us 0, then they're perpendicular. If it gives us 1, then they're parallel. If it gives us not 0 and not 1, then it's neither. And actually, there's a little bit more to it for parallel. Perpendicular is easy, it's 0. For parallel, you can have plus or minus 1. But then also you have to have the magnitude of n1 times the magnitude of n2 has to also equal plus or minus 1. So there's a little bit more checks to see if a thing is parallel. But it turns out in this one we don't have to do too much work, because if you take the dot product of these two vectors, at least the two I had, I got 0, and then therefore it's perpendicular. So mine weren't too bad. So again, dot product, you would multiply 7 and negative 24, you would multiply 28 and 48, you would multiply 21 and 56, and then you would add those up. And in my case, it turns out to be 0. Okay. Okay, for problem 10, it says consider the following planes. They give us two planes. It says find parametric equations for the line of intersection of the planes. Okay, so to do this one, it's pretty similar to how we started the last one. We're going to have an n1 vector, which is going to be the coefficients of the numbers in front of x, y, and z of the first plane. So it's just 1, 1, 1. Then we're going to find n2, which is going to be the coefficients of the second vector, which is 1, 5, and 5. And then we're going to find the cross product of those two vectors. And if you do that cross product, for my numbers, I get 0, negative 4, positive 4. And those numbers are going to be A, B, and C. Okay, then we're going to try to solve for one common point between the planes. So basically, we're trying to solve these three equations. X equals AT plus X0. Y equals BT plus Y0. And Z equals CT plus Z0. We know A, B, and C, so we could get half of it. but we need x0, y0, and z0, and that has to be a point on both planes at the same time. So to solve for those, we're going to let z equal 0. Now this is just one way to do it. There's more than one way. So let's just say, okay, let's force z to be 0. Then we look back at our plane equations and we get two equations. We get x plus y equals 4 because z is 0, so it's gone. And then from the second equation, we get x plus 5y equals 4. Okay? And what you can do is you can say, all right, let's subtract the second equation from the first. You'll get x minus x, so x goes away. You'll get y minus 5y, which is minus 4y, equals 4 minus 4, which is 0. And the only way some number times y equals 0, it must mean that y equals 0. Okay, so if y equals 0, then in either equation, it just goes away, and that means x has to equal 4. So the unique point that's on both of these, when we force z to be 0, is 4, 0, 0. And that would be our x0, y0, and z0. So if we plug those in, we have x is equal to at. A was 0. 0t plus 4. Y is equal to bt. B was minus 4. But y0 is 0. And z is equal to positive 4 times t plus z0, which is 0. So these collapse to just x equal 4 right there. Y equals minus 4t right there. And z equals positive 4t right here. So that would be the first answer. Now the trickier part, maybe trickier, maybe not. We have to find the angle between the planes. So to do that, we're going to take n1. So to find the angle, it's going to be the arc cosine of n1 dotted with n2 divided by the magnitude of n1 times the magnitude of n2. And for my numbers, n1 dot n2, so again, if you multiply the first with the first, the second with the second, the third with the third, and add them all up, for me, I get 11. Then the magnitude of n1 is just the square root of 1 squared plus 1 squared plus 1 squared, which is the square root of 3, so it's just the square root of 3. The magnitude of n2 for my numbers is the square root of 1 squared plus 5 squared plus 5 squared, which is the square root of 51. Okay, and if you do this, so my angle turns out to be the arc cosine in degrees, so make sure you're in degree mode, of 11 divided by the square root of 3 times the square root of 51, and that turns out to be approximately 27.2 degrees, which is right there. Okay, I think that's all I need to show for problem 10. Okay, for problem 11 it says find symmetric equations for the lines of intersections of the planes. So for this, we're going to again find that common point where they common point that's on both. So we can do it just like before. We're going to let z equal 0. So for the first one, we're going to get 6x minus 4y equals minus 6. And for the second one, we're going to get 4x plus y equals 7. So the z's have gone away, and we get two equations that look like this. Now there's multiple ways. This is two equations, two unknowns. There's multiple ways to solve it. I'm going to solve it using substitution method for this one. So we're going to solve for y. So this y from equation 2 would be 7 minus 4x. Then I'm going to take that and replace it into this y right here. So let's start there. We would have 6x minus 4 times y, but y is 7 minus 4x equals minus 6. This would be 6x minus 28 plus 16x equals minus 6. This would be 24x equals minus 6 plus 28. Not 24, 22. And we get 22x equals 22. Kind of nice numbers there. X equals 1. Divide both by 22. Okay, now we're going to plug x equal 1 back into the original two planes. Or either one, honestly. Let's just put it into the first one. So if x is 1 into the first plane, we're going to get 6 times 1 minus 4y minus 4z equals minus 6. And so we're going to get 6 over here, which is going to add, it's going to subtract. So we're going to get minus 4y minus 4z equals negative 12. So when I move this positive 6 over, it becomes negative, get negative 12. We can divide all three numbers by negative 3, so we're going to get, let me write it. Divide all three numbers by negative 4, and we're going to get y plus z equals 3. And we can basically subtract, we can get z on one side, y on the other, and we'll get y minus 3 equals negative z. So we're going to move this z over, it becomes negative, move the 3 over, it becomes negative, and the answer is this one. So we forced x to be 1, we just solved y, that's the same as y minus 3, and that's the same as negative z. Okay, so we set one variable, in this case z equal to 0, solve for one of the letters, in this case x, back substitute, and then we get a relationship between y and z. That's problem 11. Okay, for problem 12, it says find parametric equations for the line through the point 0, 1, 2 that is parallel to the plane x plus y plus z equals 5 and perpendicular to the line x equals 1 plus t, y equals 1 minus t, and z equals 2t. Okay, to do this problem, we are going to again create two vectors with the coefficients of these numbers. So we have n1 is just 1, 1, 1, the numbers in front of x, y, and z of the first plane. Now for the second plane, it's in parametric form, so we have to solve for for the parameter t. So we're going to have t is equals to, so rearrange each of these equations underneath the comma. So, and I'm going to add a step. It's going to be x minus 1, so move this 1, I'm solving for this t right here. So move this 1 over, and I'm going to divide by 1. You'll see why I do that in a second. That has to be equal, solve for this t. Well, it have to be, move the t over, so t is equal to 1 minus y over 1. And then solving for this t, I just have to divide z by 2. So z divided by 2. Okay, so that is going to give us, if you recall, we had the equations x minus x0 over a has to equal y minus y0 over b, has to equal z minus z0 over c. And the perpendicular plane then, n2 we'll call it, has to be the a, b, and c, which are just the denominators of these three equations. So that's why I wrote divide by 1, divide by 1. So a is 1, b is 1, c is 2, based on matching these equations. Okay, and then we're going to take a cross product of those two vectors like we've seen before. So take n1 cross n2. And again, I'm not showing that step, but if you do that step, based on the section we've done in the past, you should get 3, -1, -2. Okay. Okay, so that's the vector we want to work with, and the original point that we want to go through is x0, y0, z0, right here. And so now we're going to write these equations a little differently. We're going to write this as x equals at plus x0, y equals bt plus y0, and z equals ct plus z0. But the a, b, and c we're going to get from this new vector we just created. So this is now the a, b, and c we're going to use. So we're going to get x equals 3t, and the x0, y0, and z0 come from this one. And x0 is 0, b is -1, y0 is 1 from up here, c from this vector is -2, plus z0, which was 2 from the original point. So once you simplify these, you will get 3t for x, which I wrote right there. You'll get -t plus 1, -t plus 1, and you'll get -2t plus 2, -2t plus 2. So that's how you'll solve that one. Okay, in 13 they want us to calculate the distance between a point on a line L that passes through points Q and R, and the distance D from the point P to the line L is, so let me see if I can draw this. We have 2 points and they form a line, and one point is Q and one point is R. And then we have some point P out here somewhere. So P is not on this line L. So this is line L from Q to R. And we want to find the distance D from the point P to the line L is given by this. So we want to find this distance here. And notice it involves a cross product because the shortest distance should be perpendicular to this. Okay, so we want to find that distance D, this red line. And luckily for us, they gave us the equation, so it's not too bad. Okay, so what we have to do is we have to find 2 lines. And what we're going to find is line, I really need color here to help. We're going to find the lines QR. So we're going to find this vector here, and then we're going to find the vector QP. We're going to find the vector QP. And if we take their cross product and divide by the magnitude of, okay, so let's see which one. So A is QR, so this is A. And B is QP, so here's B. So we're going to cross product those, which gives us the area, no, not quite. We're going to take the cross product of those and then divide by the magnitude of A, and that should give us this distance here. So, so here's how we do it. So let's first find, so let's label these. So we're going to call this point P, 5, 1, -3. Now then they give us this plane that Q and R sit on, and it's parametric. So we're going to let T equal different values. We're going to let T equal 0, and we're going to solve for the point, and we're going to call that point Q. So when T is 0, X would be 2. So just get rid of T here. When t is 0, y would also be 2. And then when t is 0, z would be 3. So that's point Q. Now point R, we're going to let t equal 1, just some other value. Pick easy numbers like 0 and 1. So when t is 1, R would be 2 plus 1, which is 3. It would be 2 minus 2, which is 0, just replacing t with 1. And 3 minus 3, which is 0. And notice that those are pretty nice, easy numbers to work with. Okay, now we have to find A, which is the vector from Q to R. So just take the values in R and subtract the values in Q, and you should get 1, -2, -3. B is going to equal the vector from Q to P. So take the numbers in P and subtract the numbers in Q, and you should get 3, -1, 0. Okay, and then we need to find the cross product of those two vectors, A cross B, and if you do this, you should get -3, -9, and 5. Then we need the magnitude of this cross product, which is the square root of -3 squared plus -9 squared plus 5 squared, and that's going to give us the square root of 115. Then we just need the magnitude of A, which is the square root of 1 squared plus -2 squared plus -3 squared, and that's the square root of 14. And then the formula just says take the square root of 115 and divide by the square root of 14, and those don't simplify, so at the end you're just going to take the ratio of these two things. Okay, so a little bit of work there, but hopefully if you follow my steps you can do the same approach with your numbers and be fine. Okay, problem 14. There's an equation in the book that says you can also calculate distance from a point to a given plane, and for some reason they switch letters. They call it capital D, that's fine. And it's the absolute value of A, x1 minus x0, plus B, y1 minus y0, plus C, z1 minus z0, divided by the square root of a squared plus b squared plus c squared. Okay, and it turns out that in a plane, these numbers in front of x, y, and z are a, b, and c. So we know a, b, and c are 3, 2, and 6 respectively for this problem. So I've got the a's, b's, and c's. Now, this point we're going to call x0, y0, and z0. So that's what we call point 0. Okay, so we have A, B, C, x0, y0, and z0. The only thing we need is x1, y1, and z1. If we can get one more point on the plane, we will have everything we need to plug and chug this problem out. So we just need any other point on the plane, and so let's do our old trick. Let's force z to be 0. Okay, if I plug z as 0 into this plane, I get 3x plus 2y equals 5. And that's one equation with two unknowns, so I have to force another variable to be a number. But you might notice if x is 1 and y is 1, that will equal 5, which means the point x equal 1, y equal 1, and z equals 0 has to be on this plane. So point 1 is going to be equal to 1, 1, 0. So we just kind of looked at this and said, oh, wait a second, 3 plus 2 is 5. So let's just make x1 and y1. And then z was 0. So that's our point 1. So this is x1 y1, z1. Now, putting it all together, the distance is going to be the absolute value of a, which was 3, times x1, which is 1, minus x0, which is also 1, plus b is 2, times y1, which is 1, minus y0, which is negative 4, plus c, which is 6, times z1, which is 0, minus z1, which is, minus z0, which is 5, absolute value of that, divided by the square root of 3 squared plus 2 squared plus 6 squared, a, b, and c all squared. In the top, you're going to get 3 times 0, which goes away, 1 plus 4, which is 5, so let's write this. You get 0 plus 10, because this becomes positive 5 times 2, and then you get 6 times negative 5, which is minus 30. On the bottom, you're going to get the square root of, in my case, 49. So on top, we get 10 minus 30 is negative 20, but it's absolute valued, and divided by the square root of 49 is 7. The absolute value of minus 20 is positive 20, and the denominator is 7. They do not simplify. The answer is 20 over 7. So that would be the distance from that point they gave us to the plane 3x plus 2y plus 6z equal 5. And that's problem 14. Okay, last problem, problem 15. Determine whether the statement is true or false. A linear equation ax plus by plus cz plus d equals 0 represents a line in space. Note, it represents a plane in space. So all they had to do is switch one word and that would have been true, but the way they have it is false. That's chapter 12, section 5.